I'll try to very briefly talk about random walks, since I think this is probably familiar to most people. But the generic problem in classical statistical mechanics is to calculate properties of the Boltzmann distribution. You can see my mouse here, right? Up here, that calculate integrals like that. That's the partition function, where V of R is some potential energy function. KT is the temperature, and R is the phase space. For this talk, it'll be the particle positions. I'm sorry, there's hammering going on here. It's difficult to just sample that directly with Monte Carlo, because if you sample from a uniform distribution, then the overlap is exponentially small, where n is large, the number of variables. So Metropolis in 1953 introduced what's called random walk methods, this famous paper, which I hope everyone is familiar with. And basically the idea is, if S is the state of the system, the random walk consists of inventing some transition probability P for moving from one point to another, and then just repeatedly applying this moving rule to the state of the system. And then you have this sort of so-called master equation here that describes how the probability distribution evolves as a function of iteration, small n here. The stationary states are then eigenfunctions of this transition probability, and in particular, eigenfunctions with eigenvalue 1. And you can show without too much difficulty when it must converge to an assumed distribution. This is in contrast to something like molecular dynamics, where it's difficult to prove these things. There's definite rules about how you prove it. And you can show that, in fact, the convergence, if the system is ergodic, then the convergence is geometrical and monotonic. So the Metropolis algorithm combines these things together. We have an ergodic random walk. Ergodic means you can go everywhere in phase space. You determine that the random walk is going to the state you want by using the detailed balance principle, which is right here. Pi of S here is the desired equilibrium state, like the Boltzmann distribution. And basically, you want the probability to move from S to S prime. There's a rate balance between moving from S to S prime and S prime to S. If you have this rate balance, then you can show that the pi has to be the equilibrium state for this transition probability P. It's all fairly straightforward. And the way Metropolis, their insight was to use a rejection method in order to achieve the detailed balance. And this is the formula that, sort of the optimal formula to use. You make some transition probability, T, to moving from S to S prime, a trial move, and you can choose a variety of trial moves, and then you accept or reject the trial move based on this probability. And this then will satisfy detailed balance. Of course, this under some conditions, well-defined conditions, this has to converge to the state pi of S. However, the rate is not determined, and that's something kind of empirical. There's a lot to be said about the rate, but a lot of problems in electronic structure, there's not really a big issue about it converging slowly or whatever. Okay. That was my very brief introduction to classical Monte Carlo. what follows in the quantum Monte Carlo. I guess I could ask for questions here. But let me just continue if there are no questions. Quantum Monte Carlo. Well, the Metropolis method solves the problem of calculating properties in thermodynamic properties for classical systems where you know the potential energy, but in the real world, of course, the classical potential energy is determined by quantum mechanics. And we don't know the so-called Born-Oppenheimer energy necessarily. We have to determine that from quantum Monte Carlo or from some other quantum theory. So I'm going to talk about, there are many types of quantum Monte Carlo. And of course, in an hour, I can only touch upon a few things. In contrast to the previous lecture, I'm not going to talk about discrete models. I'm only going to talk about continuum models. That is, where the state space is a continuous variable. Typically, we put the particles in like a periodic box or something, or in a molecule or whatever. I mean, most of my work has been done in condensed matter system where we put it in a periodic box. And so I'm going to talk about three different methods very briefly. The first is Pathetical Monte Carlo. That's in a way the most intuitive and the closest to a classical problem. And the second are Variational and Diffusion Monte Carlo that are ground state methods or single state methods. And these are very much like the previous talk, right? In fact, they're the ancestors of what he was talking about previously. We can treat something like 100,000 bosons with these methods, or 1,000 fermions without too much trouble nowadays. And I like to do the continuum problems because those, of course, are much closer to experimental systems. I mean, a big problem with the lattice models or finite basis set models is achieving the so-called basis set limit. That is, how well do they converge in the number of basis functions required. So we work directly in continuum. And well, you can say in practice, our basis set is the precision of the computer, which is 1 part in 10 to the 16. So basically, it's sufficiently well converged. Okay, so first of all, with the path-integral method, path-integral methods are based on this Feynman's imaginary time path integrals. And he sort of introduced this based on previous work, of course, in 1953 also with this theory of superfluid helium. Okay, I'm going to talk about applications in my talk. Okay, so what do we want to do when we want to simulate a quantum system at a finite temperature, not a ground state? Okay, what you want to sample for thermodynamic properties is what's called the density matrix. And I'll introduce that in a second, but this is the so-called density matrix here, a simple rho of R and beta. And if you want to calculate, say, the potential energy, this V of R, you have this is the expression that you use. It's just like the expression for classical statistical mechanics, where you have an integral over the Boltzmann distribution. Replace the Boltzmann distribution by the density matrix. And this is possible because the density matrix is a positive function. So what is the thermal density matrix? Well, this is our Schrodinger equation right here, the first line. I assume you can see my mouse. Is that correct?
Yes, that's correct.
Yes. Okay. Okay. So here, this is the many-body Schrodinger equation, which we cannot solve, but we don't need to. I'm just defining the density matrix. Phi of alpha is the exact eigenstate, and R is the phase space. That is, in this case, in this talk, it'll be the particle coordinates. If we have n particles, R1 up to Rn. Okay, so then you thermally populate so phi squared, of course, in quantum mechanics, is the probability of being at a point R, and then you populate your state alpha according to the Boltzmann distribution. So this is the simply probability of being at point R in a quantum system at a temperature, inverse temperature beta, right? Okay, you could write this in operator notation, is the density matrix is just the exponential operator. Okay, but what we actually need is the off-diagonal density matrix, which is instead of taking phi squared, we open it up into phi of R prime and phi of R, and still thermally populated. Okay, the property that we need is the fact that written in operator notation, a product of two density matrices is a density matrix at a lower temperature, right? This is the convolution property of Green's functions. Or you can write it in integral notation this way, right? And from this, you can show that the off-diagonal density matrix, if we don't worry about Fermi statistics, is also non-negative, right? Okay, which is a key property. This is for non-relativistic quantum mechanics, I should say. Okay, now why does that help us? Well, if we just do this unfolding in time, m times, we're guaranteed to get the density matrix. So we have this so-called Trotter's formula, right? The density matrix at a temperature. Okay, so this is the density matrix at a inverse temperature beta, right? If we expand it out, this is the kinetic operator and the potential operator. Okay, if we expand it out m times, and then we take the limit as m goes to infinity, we recover the density matrix. I mean, it would be true if these were numbers, but it's also true if they're operators under certain conditions that Trotter proved in 1959, right? Okay, so why do we do this? We do it because these two operators, the exponential of these two operators, we can write down the explicit formulas for them, and we get these as results. The potential, of course, is very simple because it's a diagonal in R space. We're going to write these operators in R space. And the kinetic energy operator turns out to be a Gaussian in R space. I mean, it's basically, why is it a Gaussian? Well, it's a Fourier transform. You do it by Fourier transforming, and you take a Fourier transform a Gaussian as a Gaussian, and that's what this Boltzmann operator is. Is e to the minus k squared. But anyway, now the reason this formula works is that the error for a finite m, I should have written m, not n here, but is proportional to the commutator between t and v, and you get a tau squared because you have a tau in front of the t and a tau in front of the v, right? And so in the limits tau goes to 0, the commutator is just an error term, and it goes to 0. So that's why you get Trotter's formula, right? Okay. So the net result is that in order to do a quantum system, what we have to do is an integral over imaginary time path. So we write S is equal to the action. S is going to be these two things right here, the logarithm of these two things right here, kinetic potential operators. And that's right here. So this is the Gaussian term here, and this is the potential term right here. And we can say that the quantum partition function is the integral over all paths of e to the minus action of the path, that is, probability of the path. And it's easy to understand in a picture. This is a picture of 6 helium atoms in 2 dimensions in this box. This is a periodic box, like a torus. Okay, so that this path corresponds to that. This path is like wallpaper, right? Okay, so we have 6 helium atoms in here, and their initial point on the path is the black dot, and then the curve is the path in imaginary time, the other points in the path, right? And we have an explicit expression that I showed on the previous view graph of what the probability of this path is. It depends on, first, how stretched out this thing is. It's just like an elastic rubber band, right? And the second thing is the potential. That is, helium atoms interact with potential. They don't like to get too close together. So no two black points can get very close together. They have a potential energy. It's also true of every point on the path. That is, this point on the path cannot get too close to that point on the path, or this point, or that point. And so this is an exact mapping of the quantum statistical mechanics of these 6 helium atoms onto a classical problem of 6 rubber bands with a certain probability distribution, which we know. We know the interaction between the helium atoms, and we know what the action is for these paths. And the Metropolis Monte Carlo, Markov Chain Monte Carlo, is simply to average over all possible paths of these 6 atoms, or 6 rubber bands, and to calculate, say, the average potential energy, where you just calculate the average potential energy of these rubber bands. Now, the paths start and end at the same place. That's because to calculate many properties, you want the trace of the density matrix. So that means the path has to return to its starting place. As the lower the temperature, the longer the rubber bands get. And then they start to interact with each other. And that's when the entanglement in quantum mechanics comes in, when these different paths start running into each other. So lower the temperature, the real temperature in the quantum system, the longer is the rubber band and more spread out is this wave packet. Okay. There's one more wrinkle in all of this, which is the interesting part. For quantum many-body problems, not all states are allowed, only states that are totally symmetric or totally anti-symmetric. And this is the origin of things like Bose condensation, superfluidity, topological properties, and so forth. And the way we deal with this, and the way Feynman dealt with it, is to use the permutation operator to project out the states of a correct symmetry. So for bosons, you just simply take, you say F is your off-diagonal density matrix, and use you sum over all permutations, and you construct a new density matrix, which is now symmetric, right? So this is the partition function right here, is integral over all paths, and now it's also summed over all permutations. And so this means the path closes on itself with a permutation. And now the Monte Carlo task consists of not only doing the integral over all possible paths, but also the sum over all possible permutations, right? So here's the picture again of your 6 helium atoms, except now a new feature has been introduced. Instead of the paths just closing on themselves like that, you are allowed to have paths like this. And this is an unusual path because not only do you get this permutation, 1 goes to 2, 2 goes to 3, and 3 goes to 1, but it also goes through the periodic boundary conditions and comes out. This is like, again, this is like on a torus. So this is the path that goes around the torus. And you would say, this is topologically different. And that's the interesting thing, because this is superfluidity. and also Bose condensation. When you get these kind of paths appearing, it changes how the quantum system responds. For example, the analogy I use, you're probably all familiar with what Jello is, at least in this country, gelatin other places. You know, if you take Jello from the grocery store, it's a nice powder like sugar. Well, it's mostly sugar anyway. But anyway, you pour it into the water when you're cooking Jello, and it just makes a nice, red liquid or whatever like that. And then you cook it, and then you cool it down, and then it's changed completely to a very elastic solid. You can turn the bowl upside down, and you'll get, it won't flow all over the counter, right? Why is that? Well, it's because in the cooking process, the gelatin molecules have hooked onto each other and made a backbone through the water. And there's one giant molecule which has completely different elastic properties than it did before it cooked. And so superfluidity is exactly like that, except it's also exactly opposite because we're in imaginary time and not in real time. So a superfluid system, if you shake it, it does never respond, whereas the Jello does respond. So anyway, that's because of the imaginary time. So anyway, that's an example of the kind of physical insight that we got from path integral Monte Carlo. And I think that's the end. Oh, there's one more point before I stop for questioning. For Fermion systems, you have exactly the same formula, except for the kicker is you have this -1. You have the signature of the permutation that comes in there, -1 to whether it's an even or odd permutation. This, of course, changes everything. And fermions are completely different than bosons. Bosons always like to be together. Fermions cannot stand to be together, right? Most particles in nature are fermions, like electrons and protons and neutrons. So basically, you could do the so-called direct method is you could just simply go ahead and run your boson code, and you would count this path would count positive because it has an even number of exchanges, right? It's positive. It's a positive permutation. But if just these two atoms were permuting, you would get a minus sign, and you would count that as a negative walk, whereas this is a positive walk. And so, if you wanted to calculate a process of a expectation, it would be the positive pass minus the negative pass at when you calculate averages, and that's the so-called Fermion sign problem, which is the notorious problem in this field. And basically, you can show without too much trouble the computer time needed to give an accuracy epsilon would scale like this. It is mathematically a correct calculation. Your error bars, however, grow as the temperature goes to 0 or as the number of particles goes to infinity, exponentially fast. And this is the expression you can easily figure out with the direct method. That is, if you just try to use your boson code to do fermions. And so basically, you're going to get huge error bars for any interesting problem. Although, you can sort of do things at high temperature, that is when T is big, or we're just like, 5 or 10 fermions, you could do that, but you can't extend it in general. So that's the sign problem. So I think before I switch into something else, does anybody have a question about path integrals? We use this for hundreds of particles. And in the case of helium, we've done like 10,000 or so. It's a standard algorithm. I think later in the week, you're going to hear more about this applications in chemistry. But anyway.
We have a question online.
Online.
Yeah, why don't you go ahead with your question?
Hi, I had a question regarding the action. So this path integral implementation, does it assume the action to be conservative, or it can also work for non-conservative actions that we have, like environment or like kind of?
Well, I've assumed that it is conservative. That is, it's just simply, this thing is just simply a potential energy V of R and a non-relativistic kinetic energy. Okay. You're talking about, you could also do a problem like a polaron, where it's non-local in time. That's also been done, right? Where I think this is similar to what you're asking about. So you could do that actually, where you have some other degrees of freedom, and you can analytically integrate them out, and you have a more complicated action in that case. It's this action is local in time, in imaginary time. That is, that it depends only on, connects neighboring points on the path, right? Yeah. And for example, the potential energy only is instantaneous in time. But if you like integrate out some other degrees of freedom, you would have an action which becomes non-local. And this would become more complicated form anyway. You could do it that way. Now, what you don't want to do is integrate it out and end up with a minus sign, right? Yeah. Then that becomes a much more difficult problem.
Just one question. So for like a non-local potential in time, if we have them like exponentially like decaying, is it enough to be able to use this, or it should be even like faster decaying? I mean, so obviously what I learn here is just this is local in imaginary time, and you mentioned that there are other ways to also mitigate like some kind of non-local. So that non-locality should be exponentially like decaying,
I don't think it has to be. If it's exponentially in time, then presumably the algorithms that we use already would be fine. Even if it's slower decaying, like algebraically, formally, things should work okay. They become more complicated. That means because this is local in time, then you can make a metropolis step, and you only have to evaluate the interactions at that time step, right? You don't need to look at the whole rest of the path. But if you had a non-local in time, you would have to look at everything. We actually, when you make a move, like to do a superfluid system, you actually do. It's a good idea to look at the whole path and not just at the local time. So it wouldn't be a big change, but without looking at the details, I couldn't say more.
Thank you. Thank you.
Any other questions right now? Okay, I think we're good to proceed.
Oh, okay. The first major QMC calculation was done by a graduate student here at the University of Illinois, Bill McMillan, in 1964. And he developed what we call Variational Monte Carlo, which is exactly what the last speaker talked about at the end of his talk. And he was doing this system of helium atoms. It's like a Lennard-Jones system. I hope you know what that is, just particles interacting with a R6, R12 potential. And he simply applied the then developing techniques to do liquids, the Metropolis Monte Carlo, in this famous paper in 1964. Actually, in my thesis, 10 years later, I sort of generalized this to fermions that I'll talk about a tiny bit about. So I think the previous speaker did discuss variational Monte Carlo. And basically, you take a trial wave function, psi, which has a known analytic form. That's the problem with it. Okay, and this is the Rayleigh-Ritz principle. The upper bound to the ground state energy is, I call it EV, right? And so basically you just sample psi squared using Metropolis or Markov Chain Monte Carlo. Okay, and then to calculate this integral here, you calculate the average value of the so-called local energy, which is given by this expression, which you have an analytic expression for, right? Because psi of r is a known function, and you calculate h, which for a non-relativistic Hamiltonian involves calculating the second derivative of it and the potential energy. And you're guaranteed to get an upper bound. So then you try to optimize this wave function to get the best upper bound. Now, the variational principle does rely on assuming some properties of the wave function. It has to be, if you're in the continuous space, it has to be a continuous function. You're not allowed any arbitrary function because you have to be able to take the second derivative of it. It has to have the proper symmetry, that is Bose or Fermi symmetry. Well, for bosons, it doesn't. Anything, the boson wave function always has lower energy, so you always get an upper bound. It has to be normalizable, namely, so you have these two integrals have to exist, and very convenient for quantum Monte Carlo, it has to have a finite variance. Now, the variance is defined as this integral, where you have an h squared here instead of just a single Hamiltonian, right? And as the previous speaker pointed out, there's the so-called zero variance principle, which is as this wave function goes to an exact eigenstate, then the sigma squared vanishes, and usually vanishes the same way, as I'll show you, as the energy does to the exact energy. And anyway, so that's variational Monte Carlo. So now what kind of wave function should we choose? Well, there is a standard choice. This is for bosons right here. And it's called a Jasper wave function after the third person that discussed this in the 50s. Beale was the first person, but he died in the Second World War, so he doesn't get as much credit. Basically, if you consider particles like hard spheres in a box, what would you expect the wave function to go like as any two particles get close together? The wave function has to go to zero. So you want a product type of wave function like this. And U of R here, which is called the correlation factor, it is a variational function. That is, you try to choose U of R to get the lowest energy. That's what we're doing variational Monte Carlo. And the local energy, which I defined over here, local energy is the error in your trial wave function, basically, would be explicit. If for a pair potential, would have this explicit form. It's given by lambda is h bar squared over 2m. So now, if you have a good wave function, this local energy should approach a constant that is independent of position. Okay, so you can analyze it to figure out how U of R should behave in certain limits, namely the limit as R goes to 0 and R goes to infinity. R goes to 0 is particularly simple. That gives you what's called the Cusp Condition. It tells you how basically the many-body wave function has to approach a solution to the two-body wave function, which you can compute. And that's the Cusp Condition. But sometimes I discussed over here that you want to have a finite variance, and that places certain limitations on this trial wave function psi. That this integral has to be finite, not infinite. But these are easy to figure out. Okay. And now, what do you do for fermions, like electrons? Well, basically, yesterday you heard about Hartree-Fock. Okay, that's where you start out. You take a wave function. Oops, sorry. You take a wave function, which is this is for a liquid. You have a determinant of plane waves, and then you have a spin function here for spin up and spin down. This becomes your wave function. And if you have a periodic box, then this k value, the momentum for the orbitals, is quantized, right? And the 2 pi over n, and we deal with what's called twisted boundary conditions, where we can add a phase factor twist to the wave function. And so now if we want to generalize this to interacting systems, instead of just free particles, we multiply by this Jasper factor. So we put correlation directly into the trial wave function. And this is the enormous advantage of variational Monte Carlo. That is, Hartree-Fock is by definition uncorrelated electrons. Electrons only see the average behavior of other electrons. They don't see exactly where the other electrons are. Okay, but with a Slater-Jasper wave function, if one electron is here, then the other electron, then the wave function changes for the other electron. It wants to avoid that electron. That's the Jasper factor. So again, this U of R would be a variational parameter, that is, and you can figure out how it should behave at small r and large r analytically. But dealing with this wave function, you can't, in Hartree-Fock, you could do the integrals, you could calculate the integral, the energies and properties analytically. But once you put in the Jasper, it becomes like a classical statistical mechanics problem. You have to use Monte Carlo, and particularly variational Monte Carlo. Now, the only trick with fermions is you have to deal with determinants, and there's a matrix update rule that gets you a factor of order n in the speed. It reduces the complexity, but that's a technical detail. And so the algorithm is like DFT. It's order n cubed to move all of the electrons, and or to do 1 million steps of all the electrons. The only difference with DFT, of course, is you have an error bar. But on the other hand, in contrast to DFT, you don't have a basis set limitation. Now, here's one of the only examples of output I'm going to do. Here is the electron fluid. This is actually the input to all DFT calculations, is the correlation energy of the electron gas, which was calculated with quantum Monte Carlo. And basically, this is a plot, we have the energy, which is an upper bound on this axis. And on this axis, we have the variance of the trial wave function. Hartree-Fock would be up on the 3rd floor, way up here. And then as we get better wave functions, we come down to where we think the ground state wave function is, the exact answer is here, right? So here's Slater-Jasper. And then the advantage of variational Monte Carlo is you can add more terms to the wave function, like was done in the last talk. You can add what's called 3 body terms, backflow terms, and so forth. And you get better wave functions. You get both better energies and better variances. And for various reasons, it usually falls on a line here if you optimize things correctly. And the next method I'm going to talk about, Projector Monte Carlo, you end up over here. You get lower energies, which just automatically optimize things. So I'll discuss this next. But does anybody have a question about, about variational Monte Carlo? As the previous speaker emphasized, it's an extremely powerful method because you make a physical ansatz for the wave function, you optimize things, and you get an upper bound, and you get lower energies, you think you're doing better. The scaling is almost classical. Those determinants are in cubed. Of course, until you get to hundreds of electrons, the determinantal part is not dominant. The Jasper part is more important. But when you get up to thousands of electrons, then it becomes n cubed. It doesn't have a sign problem. The optimization, however, is rather time-consuming. The energy is insensitive to the order parameters. Non-energetic properties are less accurate, and it favors it. There's a bias. You're doing a phase transition, like liquid, solid, polarized, unpolarized, or whatever. It favors simple states over more complicated states, so it biases the results. So you need a more accurate method, which is the motivation for what I'm going to describe next. But are there any questions about VMC right now?
Just like a very general question in case I missed it. So how exactly is the wave function then constructed?
How exactly? Well,
what are the basic methods?
Okay. Fundamentally, we start out with Hartree-Fock or DFT. This is for electron problems, okay, electronic structure problems. And you learned about that yesterday, like Hartree-Fock or DFT. And that gives you orbitals. If you have n electrons, it gives you n orbitals, right? Expressed in some numerical basis, like plane waves or Gaussians or whatever. Okay. Then you want to add correlation. And you just simply add this Jasper factor here. And the Jasper factor could have an electron-electron term, and it could have an electron-nuclear term. And you know what the properties of that Jasper factor are at small r and large r. It has to be a continuous function with known properties at r equals 0 and r equals infinity. So usually you make like a simple Pathetical approximation to that, or use a spline function to express it. And so there's a certain number of parameters, and then you optimize those parameters. And I'm not going to discuss it, but there's optimization methods a lot like what the last speaker talked about, right? To optimize these. But the only difference is we have to worry about the continuity of the wave function. Right? So if you're working on a lattice model or a chemistry problem in a basis, you don't have to worry about the continuity. Those are just numbers. But here they're functions you're optimizing. And if you want to go beyond that, you can do things called backflow. And the philosophy is, it's called, I don't know if I can find that slide, but there's something called the Feynman-Katz formula. It tells you what the wave function is in terms of the potential, in terms of random walks. And you can use that to take a local energy and suggest new forms for the wave function. And that's where backflow came from. And then there's even something called iterated backflow, where you take a wave function and you make an improved wave function, improved functional forms. So the backflow would be follow on here. And you can iterate that many times. That's one approach. Another approach, which is being pursued more now, is expanding out this determinants into multi-determinants. And so this is yesterday, Karen Burke talked about configuration interaction. We have multiple configurations of chemistry. The thing is, with a configuration interaction, you don't have the Jasper factor, so you need millions of determinants to get the electron correlation. Here you have the Jasper factor, so maybe you only need a few. If you can expand in determinants, then maybe you only need 1,000 determinants because you have this Jasper factor helping you also. Okay, so does that help you?
That really answered my question. Thanks.
We have a question online as well. Hassan, you can go ahead.
So I just had a quick question. So can these trial functions have like a finite number of discontinuity, or they should not have any discontinuity?
Well, okay. In general, they shouldn't have discontinuous. They could have a discontinuous first derivative. The thing is, you have to calculate the second derivative, right? Now, mathematically, I mean, you could say you're dealing with delta functions, but you may not want to go down that road, because then you have to not only integrate over continuous spaces, but you have to sum over the places where the function is discontinuous if you have delta functions. So you may not want to deal with the discontinuous functions, but you can, of course, have a discontinuity in a place where the wave function must vanish, right? Like if you have hard spheres, you will have discontinuity at the hard sphere radius, but the potential is infinite there. So the places where the potential goes to plus infinity, that's okay. Anyway, you have to analyze it.
Okay, I don't see any more questions.
Okay, thank you for those questions. Okay, so when should I finish by?
You have about, you could go all the way to noon our time, so another 25 minutes.
Okay.
Since we're having questions.
Okay, I'm probably going to finish earlier, I guess.
That's fine.
Went faster, but okay.
Don't worry.
The last method I'm going to talk about is the projector Monte Carlo method. And this is actually exactly like the full CI quantum Monte Carlo method that the last speaker talked about. In fact, that method, it was a direct mapping of this earlier projector Monte Carlo method onto a lattice problem by Alavi about 20 some years ago. But anyway, this is actually where I entered the scene. Kalos was my advisor and graduate student. He wrote this paper in 1973, where he solved the problem of the ground state of bosons. You can see up to 256 bosons using projector Monte Carlo. And it had been originally suggested by Fermi and other people. However, it wasn't until Kalos came along that the numerical tools were really developed to do it, okay? And now I'm going to describe a simplified version called Diffusion Monte Carlo, okay? And it's very similar to the Pathetical Monte Carlo because basically you're still using imaginary time, okay? So I talked about, with the density matrix, you had imaginary time here. This would be the same as the density matrix if the boundary conditions and imaginary time were different. So the basic idea of projector Monte Carlo is you take a trial wave function here that comes from variational Monte Carlo, and you project it for a time t, imaginary time t. There's no I here, that's the imaginary time. Okay, to create a new wave function at time t, right? Now, it's easy to see what this is going to do. If these are the exact eigenfunctions, okay, we can expand the initial wave function into this basis, this exact eigenstate basis, right? This is just an expansion into the exact basis. And then we can evaluate this projection operator in this basis, and we get this wave function at time t is an expansion of the exact eigenstates, but we see that in imaginary time that everything except the ground state will decay to zero, right? Assuming there's no degeneracy in the ground state, okay? This will project out all the higher states, okay? So the limitus at large time is the ground state wave function times this normalization factor. This normalization factor right here is just a number. Okay, if you adjust this trial energy This is the so-called trial energy here. If you adjust it to be equal to ground state energy, then this gets rid of the time dependence here, right? If you just normalize the wave function. Okay, and so you have projected out the ground state wave function. So how do you do it? Well, we do the same trick as we did before. This is Trotter's formula in a different form. This, if we differentiate this equation with respect to time, t, we'll pull down at h, right? And we will get this equation right here, right? This is the so-called master equation of the stochastic process, right? And assuming we have a non-relativistic Hamiltonian here, the kinetic and potential function, Trotter's formula implies that you can separate this master equation into two master equations, a kinetic part and a potential part, and we know how to solve these two equations exactly. This is just a diffusion process and a random walk, and this is just a growth-death process, killing and branching, duplication. But the big caveat is we have to interpret psi as a probability density. And of course, that's ridiculous because a wave function is typically complex. If it's not complex, if it's real, which you can often make it real, it has positive and negative regions, like with fermions. But for bosons, at least, we can, for the bosonic ground state, we can assume that the wave function is non-negative, and that's a probability. And so sticking with that for the moment, the way that you can do this simulation is you construct an ensemble with some population P consisting of P points in your phase space, R1 up to RP. Each R here is the coordinates, 3n coordinates for n particles. So you have a whole ensemble of your systems, P members. You go through the ensemble and diffuse each step. That's the kinetic operation. And this is a normal random number. And then you make a certain number of copies of it. And this is the number of copies, where U is a uniform random number. And this is the branching factor. You see, if you're in a region where the potential energy is very big and positive, then they'll get killed off because this will be zero. And this is the floor function. So you truncate it. So they'll end up with 0 copies. And the places where the potential energy is very negative, you'll end up with a number greater than 1, and you make a lot of positive copies, right? And so it's like sitting 100 undergraduates that happen to be rather drinking too much, and they can go uphill and downhill. And the ones that go uphill die off, and the ones that go downhill, make a lot of children or whatever and grow. And so the Schrodinger equation is an equilibrium between the diffusion and the growth-death process, right? And the trial energy is adjusted to keep the population fixed. And you calculate the ground state energy by the average potential energy. Now, the branching is uncontrolled. The population is unstable, and we can solve these problems. First of all, the branching process, this was the real intuition of Kalos in the 1970s, using the ideas of importance sampling. And basically, you take your master equation back here, this equation, and you multiply it by a trial wave function. You multiply it and you interpret the product as the thing that you want to simulate, right? So this is the product. So phi now is your unknown wave function, and psi is your analytic, your Slater-Jasper wave function. that you have from Variational Monte Carlo. And this becomes your new master equation. It's just an algebra to get this. And you do some more algebra and you can end up in this form, which is the diffusion Monte Carlo master equation. So this is just some algebraic transformations. Now you see that at large time, your distribution now goes to the product of your trial wave function times the ground state wave function, the exact ground state. And your energy is just the average local energy. And you have now two new terms. This is a diffusion term that you had before. The Trotter's formula says we can split up this into three processes instead of two. This is a scalar number, the local energy, which again goes to zero for a good wave function, the zero variance principle. And so this is the branching factor here. The branching is no longer on the potential energy, it's on how bad your trial function is. So you come up with a better trial function, you have less branching. Particular, when two electrons get close together, or an electron falls into a proton, and say that case, the electron falls into the proton, your potential energy goes to minus infinity, your branching would go to plus infinity. You would make an infinite number of copies. You put in an electron-proton Jasper factor, that doesn't happen. It's perfectly well defined when an electron goes into the proton. That's this term. But as a consequence of having this term, you have another term, which is just a drift term in random walks. That is, this is the so-called quantum force. The trial wave function pushes you away from improbable regions, and you drift away. So you have a third process.
Maybe some questions before we move on.
Yeah.
So basically, by imposing the trial wave function, we turn the wave function into a density, or
well, ideally, see, if you had, it's going to come up with the next slide. Your f function now is very much like the square of the wave function. If your psi t was close to phi 0, this would be like phi 0 squared. Particularly, if you have a Fermion system, if psi and phi have the same sign everywhere, if you have the nodes of the wave function correct, then you end up with a positive probability. So yes.
So then a good trial function would be whatever is as close as possible to
right.
phi 0.
So a very important part of diffusion Monte Carlo is to do a good job on variational Monte Carlo, so that psi t is very close to phi. And then this is like a step that polishes it and essentially improves the modulus arbitrarily well, but it doesn't do well on the nodes. So actually, you can even do complex wave functions with this important sampling. Does that answer your question?
Yeah, thank you.
Okay, I'm almost done here. So how do you do fermions? If you have, this is at least the sign problem again. You can just do it directly, namely, in fact, I'm doing calculations like this now, where you just carry along the sign of the wave function. I'm not going to discuss this, but basically that leads to a sign problem, because if you have anti-symmetric problems. One cautionary thing, it's not true in one dimension. In one dimension, you can solve the sign problem. That is, if you have electrons on a line, that's because you know where the wave function changes sign when two electrons are at the same place. In 2 or 3 dimensions, however, it's not true. Electrons can trade places without touching each other. So anyway, this direct method, the signal to noise ratio goes to 0 exponentially fast in t, and so that's the sign problem. In fact, maybe this slide is a little out of place, but this is the way I state the fermion sign problem. Basically, we want to find an algorithm if we have n fermions and a known Hamiltonian and a property such as the energy, how much time will it take to estimate the property to an accuracy epsilon? And how does the computer time scale with n and epsilon? Okay. If you can map it onto equivalent problem in StatMech, then the computer time would scale polynomially with a number of particles and 1 over epsilon squared, right? That would be a solved problem. But this is not true in quantum mechanics. Unfortunately, it can grow exponentially in the number of particles. And you want this exponent alpha here not to be too big. But the important point is there are lots of algorithms that can do this, but the approximations are not controlled. Like variational Monte Carlo is an example of one where the approximations, because you don't know how well your ansatz is. You may just be getting the best energy in that class of wave functions. Okay. So this is like the key problem in the field is which problems can be solved and which can't. There are certain lattice problems that can be solved. I just said one-dimensional problems can be solved. Bosons can be solved. For thermodynamic properties, most dynamical properties cannot be done in this sense. But what's done in diffusion Monte Carlo, so it's called the fixed node method mostly. You can do the exact methods, but mostly people do fixed node. Basically, you have a trial wave function. For the moment, let's say we're dealing with real wave functions. You just say you want your solution to have the same sign as the trial wave function, or you want it to vanish when the trial wave function vanishes. That's a boundary condition. This will give the best upper bound to the energy, and it's lower than the variational energy, the psi t, and it's closer to the ground state, basically. Basically, what you've done is, subject to this constraint, you found the best possible wave function with this constraint. So it's going to be better than psi t. Now, you haven't solved the problem in general because this f could have a discontinuous gradient at the nodal location. It scales well like variational Monte Carlo or like classical systems like n cubed. And you can generalize it from this to lattice models, finite temperature, magnetic fields, complex wave functions, and so forth. It's done. But you need trial functions with accurate nodes. And here is the same figure I showed you before, but now you have these 2 points. These are put at 0 variance. They really shouldn't be at 0 variance, but we haven't computed their variance. But if you take the Slater-Jasper wave function, this is variational energy here. If you just apply diffusion Monte Carlo, you end up with this energy. If you take backflow wave function, improvement over Slater-Jasper, you end up down here. So we think that the real answer, the exact answer, is down here. So you see you're much closer. Just by this automatic process, you do variational Monte Carlo, you get a trial wave function, the best that you can come in that class. And then you just do this diffusion Monte Carlo projector that improves the modulus of the trial function. And you get usually like 90% of the remaining energy just by improving the modulus, but not 100%. You haven't solved the sign problem. You're not necessarily the exact answer. And so this is kind of a summary of T = 0 methods. These are the golden era of applications. This is computer time on a log scale here. And this is the error in atomic in units here. And this is just some arbitrary. This was actually done for dense hydrogen. Okay. So you have a simple trial function. You do variational Monte Carlo, but you don't get the exact answer because your wave function space is not so great. You do a better variational wave function, and you get better, lower energies. But eventually you see the limitations. You apply the fixed node method with the simple trial function, you get a better answer. You get down to here. The slope is the same. It has a higher intercept because your time step is smaller. The convergence is slower. But you don't get the exact answer. But you get a better trial function. Well, maybe you got something in the golden area of application space here, where a reasonable amount of computer time got sufficiently accurate. Now, these exact methods or Fermion methods are like this. That is, they will give you the exact answer, but their slope is less. They converge slower because of the sign problem. So anyway, that's the conceptual thing. So now the latest thing is using neural networks. So maybe you get a better trial function with a neural network. You get down here better, but you also have to see how much computer time they take, right? You have to fold that in. They take a lot of computer time, I think. And so, that's not necessarily the answer for all problems. Okay. But I guess that's one of the things we're going to explore in the workshop. And so this is my summary side. Methods of classical simulation carry over to quantum systems, but they're only exact for thermodynamic properties of some quantum systems. Otherwise, they're variational, but they are the most accurate general methods around for quantum systems. And thanks to Kieran for putting up my book. I do have 4 chapters in this book that describe what I just talked about in more detail. So I'll stop there.